for the final project summary for investigating efficient tar management from biomass and waste to energy gasification processes. And Patrick Scott is going to tell us about his project and give us the final summary.
Okay, thank you very much, Robin. Thank you all for attending. My name is Patrick Scott. I've been with Lockheed about 28 years now, worked on a number of different projects. I tell people I've worked on everything from satellites to submarines, and now I can add gasifiers to that mix. We do quite a bit at Lockheed in Owego, and I've got to share in the work on a lot of the different projects and programs that we've been on. This project was initiated in 2010. The original statement of need was 12-03, waste to energy converters for overseas contingency operations. Our turn-on was in around 2013. We had a little bit of a delay behind the other folks. I think there was some bureaucracy going on between Lockheed and our customer. I'm not sure of all the details, but we got a little bit of a late start. And this work included some catalyst help from NRAL, Kim McGreeny, who is on the line, and we also had some plasma help from Drexel University with Alexander Rabinovich and Alexander Friedman. The technical objectives were to test two tar reformation technologies. One is a plasma, a gliding arc, or also called a non-thermal plasma. I always tell people it's like the Jacob's ladder you used to see in the monster movies, the horror movies, where you see an electric arc going between two copper rods that are bent apart from each other. Imagine a gas flow through that arc with a non-conductive plate, like a glass plate in the front and the back where the arc is going, and you're blowing processed gas through that. You have lots of excited electrons and molecules that are chemically reactive. And that's the basis of the gliding arc. It evolved to more of an annular approach rather than just the two rods, but that's the basic idea behind that. Is it's electrical chemical reaction rather than just thermal plasma where you're heating the bulk gas to thousands of degrees. The catalyst is the NRAL formulation. What interested me about their work is they had some that were making lots of benzene versus carbon monoxide and hydrogen. They were more poison resistant, and it seems like it was easier to make benzene than COH2. And the idea behind this was we could use the plasma with some air to attain the temperature necessary for the catalyst to work. And the goal there is to minimize the electrical input. We want to get as much chemical energy out without having to invest a lot of electrical energy back in. And the other aspect of the benzene, trying to get benzene out of this with the original concept, was that if you look at burning benzene in an engine, and benzene is one of the major, let me back up a little, it's one of the major tar components coming out of biomass gasification. So it's kind of the focus for the discussion and the thermodynamics. If you look at burning benzene in an engine, it's 190% better than taking that benzene, reforming it to carbon monoxide and hydrogen, using some of that benzene energy, and then burning that carbon monoxide hydrogen mix in the engine. And then the last aspect of the project was to look at scrubbing those streams with fuel, with JP8 or some fuel similar to that, with the idea that we could capture a number of the usable tars, the flammable liquids that come out of gasification, primarily updraft gasification, burning them directly in the engine from the liquid phase instead of going all the way to reform, to reform to carbon monoxide and hydrogen. Okay, the research driver, a little background on that. I'm sure you know a lot of this already, but on a forward operating base, the organic waste is an energy opportunity. The burn pits we hear about on TV and hear cases of soldiers and people being exposed to the fumes from the burn pits, causing health problems later in life or immediate problems depending on the level of concentration. And basically what gasification is, we're taking carbonaceous matter, organic matter, and turning it into carbon monoxide and hydrogen. We do that with the energy coming from partial combustion of that organic material to carbon dioxide and water. And then ideally the CO, carbon monoxide and hydrogen, is fed to an internal combustion engine. And when I say ICE, I mean spark or diesel, and primarily diesel engine is what my interest is in. and then that IC engine drives the generator. And in the pictorial, you can see what's going on. The feedstock comes in into the gasifier, carbon monoxide, hydrogen, other things come out. And then you also get the TARs, and that's the historic fight that's gone on with gasification from day one, is that the TARs plug the pipes, intake manifolds on your engine, and they're toxic, and they come up the works, and they're quite the headache, the Achilles heel of the whole idea. So a lot of work has been done on cracking the TARs. If you do it in just the gas phase, you probably want to be around 1200 C. If you've got a catalyst involved, I think the main thing there is it lowers the temperature to maybe 800 C. And then the plasma, like I talked about, basically you've got a couple different types of plasma where you're making active species that break down the molecules. But you still need, it turns out, considerable temperature to do that, is what you find when you get into the fine print of the plasma reactor manual. And here in this pictorial we show a kind of a basic tar molecule, phenanthrene, getting broken down into carbon monoxide and hydrogen is the idea of what's going on here. Well, as I said, the TARs are kind of interesting in terms of what they actually are, especially when you look at an updraft gasifier. From biomass, you see they're mostly benzene, toluene, xylene, some naphthalene. Most of those are flammable liquids. The largest percent are flammable liquids. You get some heavier stuff, polyaromatic hydrocarbons, sugars or cellulose fractions, waxes and other things like that. The main thing that I took from reading about this is that in an updraft gasifier, if you have reasonably dry fuel, you do get high TARs, you get lower particulates, but you get about a 90% conversion of that biomass into a gas phase. It's a tarry gas phase. It's going to condense on anything, but it is a pretty high conversion. And the key concept we had when we were thinking about this was, what do we do to maximize the waste energy delivery to the engine? That's our goal. We want maximum electricity out. Per the statement of need, they wanted as much electricity as possible and dry ash coming out the bottom of the gasifier. We'd done some earlier work where we looked at a plasma gasification system. We call it the DOPAG, Deployable Omnivorous Plasma Assisted Gasifier. And there we were looking at making a slag of the ash, and the energy balance just isn't there when you've got to put that extra energy in to make slag. So, I mean, really, I think you guys had the right idea with the statement of need, maximum electricity and dry ash coming out the bottom. And the way I looked at the best way to make that happen was use an updraft gasifier, generate a tar-rich stream, look at cracking that tar-rich stream into carbon monoxide and hydrogen, but also I show this as gold because it is kind of the gold, that the benzene, toluene, xylene, the flammable liquids that could be used in the engine. And then if you quench and scrub this right, you should be able to send the heavies out. The heavies are the nasty tars that wouldn't be liquids at room temperature. Send those back to the updraft gasifier, and after going through this, maybe that's where we want to put the plasma and catalyst, is down here on the bottom. It's not risking destroying the hard-made carbon monoxide and hydrogen. Let's send these nasties back to the gasifier. Maybe you treat them, maybe you just have a fuel oil kind of burner that burns them and gets rid of them and then puts that energy into your gasifier. But on the other side then, what goes into our scrubber then is a JP8 fuel, something like JP8 or maybe even JP8. It's going to capture the heavy tars and then pass the lighter materials, carbon monoxide, the hydrogen, the permanent gases, methane, ethane, and who knows what else, into our intake manifold on the engine. In the liquid phase, and then would be our benzene, toluene, xylene that goes in through the fuel injector. And when I look at some diesel engine manuals, I could see that we could run on 35% aromatic compound. You'll get some D-rate to the engine, but you are burning what's really garbage in your engine, which is, I think, what we really want to do here.
So if I could bust in just a second here, I have two questions.
Okay.
In terms of the heavies, you have sort of two lines of heavies. One set that you say could go straight into the into the diesel gen set and one that comes out. What's the line between those? Is it a molecular weight thing, or where do you say?
Which line now?
So, okay, I guess there's red cross. There's a red line across it.
Okay, yeah. What I'm trying to show there is that in the ideal world, we could use a plasma and a catalyst to crack the heavies, get rid of them, turn them into benzene, toluene, and xylene, and maybe some carbon monoxide and hydrogen, and then go to the scrubber and capture those.
Alternatively, you could take them back. I see now. Okay, got
it. Alternatively, if you just ran the quench right, you could knock out those heavies only, and then put them back to the gasifier where you get rid of them.
And then the other question I had is, if you do burn in a diesel gen set something that has 35% aromatics, would you think the emissions might be a little worse than a regular
They probably would be, but if you look at a JP8 spec right now, it allows 25% aromatic hydrocarbon in the fuel mix. I haven't looked recently, but the Defense Logistics Agency tracks how much aromatic is in the fuel, and when I looked at this, probably back when we were writing up the original proposal, I think it was averaging around 11%. So what that said is, if we wanted to stay within spec, we could still add, 10 or 15% of these waste products into our fuel and still stay within spec on that respect of aromatic content. And it does. The engines do allow it. You do get a D rate because it's not as energetic a molecule. If you had hexane versus benzene, you got extra hydrogen on there that's going to give you more energy, and then there's aromatic stabilization that occurs with the structure of the molecule that makes it less energy releasing when you do combust it. But again, it's quote unquote free fuel.
I'm just looking towards the future and saying if someone were to take a concept like this and move forward to a demonstration, part of that demonstration is going to have to look at the emissions as well.
Absolutely. And one thing too that I've pondered is the emissions, a lot of it you worry about is the soot. We could alter the temperature of the scrubber. We did some modeling with Aspen, and we could actually drive a considerable amount of the benzene and toluene and xylene. They're aromatic. They vaporize quite easily. They could probably be sent in through the intake manifold in a gas phase, and I bet they would burn a lot cleaner than in a droplet form where you're evaporating in the combustion chamber, rapidly you're evaporating, and this droplet of fuel gets more and more concentrated in nasty stuff, and then a little soot particle is what's finally left, which is a little piece of graphite type material. So I think there's opportunity there to look at feeding the material gas phase versus liquid phase, and then looking at what the emission output would be in both scenarios.
Okay, thank you.
Okay. I'll go through this quick. Thermodynamically, again, I talked about it a little bit. If you look at benzene or toluene, if you burned it in the engine, it's much better to burn it in the engine than it is to crack it to carbon monoxide and hydrogen. In addition to just the energy output, if you're going to reform these materials in air, you're going to have more nitrogen going to the engine. So it's really a lot better to fuel with liquid versus vapor in terms of how much nitrogen is going to the engine if you are doing the reformation. And the other thing is that cracking is high temperature. It complicates the process, makes it dangerous, requires expensive material. We want to minimize it. So what was our technical approach to this project? First of all, we needed a gasifier that could, we thought we wanted to up or down draft. If we got more fancy and more time, depending on how things work, we may want to compare the two. Feed this gasifier with a double dump valve to keep it airtight, reasonably airtight. Run updraft for the first part to get a rich tar stream filled with that energy, the benzene, toluene, xylene, and other fragments. What we did is we had it flow up through the biomass and then down through a central pipe that exposes the process gas, the raw syngas, to the combustion temperatures at the bottom to kind of reheat that stream and try to reduce condensation problems of the tar in the piping. We integrated that gasifier to the pilot plant, and that included the plasma and the catalyst bed. And then we designed and incorporated a sampling system that would do GC, gas chromatograph analysis, and then some gravimetric tar. And then we would couple all the sampling with analytic tools to try to understand the chemistry. So here's the gasifier in cross-section. I apologize for the busy charts. I'm kind of famous for them. But basically, we have a double dump valve that drops the waste product, or the feed, in front of a hydraulic or a pneumatic ram that's going to push the material to the mouth of the gasifier where it drops in. We wanted to leave a plug of material here to kind of act as a tar shield to keep tar from going back and coating all the work. So we only push about halfway, and then we get this plug of material going through. It's not an airtight plug by any means, but it did, in fact, condense the tar. The initial idea we had was to feed with electric eyes that were nitrogen purged to keep them from condensing tar on the windows. It worked on wood chips, but I'll tell you later some of the other stuff that happened when we had paper and plastic floating around there. And here's the overall block diagram. The waste comes in, goes to the gasifier. These red arrows indicate the gas chromatography and gravimetric sampling ports. And that sampling is essentially scrubbing with methylchloroform for the gas chromatography or alcohol for the gravimetric sampling. We could sample off the top or the bottom. We could do it before the plasma, after the plasma, before the catalyst, after the catalyst. And then this black arrow here indicates the gravimetric sample that simulates scrubbing with synthetic JP8 to simulate cleaning up the gas that would be coming off the top of the gasifier, or wherever we wanted to place that. We could sample with that scrubber approach throughout. So here's the piping diagram. Again, I apologize for the busy charts, but basically with the way the room was oriented that we had basically a basement. There was a garage door on this side of the room. So we wanted to have good egress in the event of emergency. So we wound up with the gasifier on this end. When we started up, we would draw the gas out through this bypass. A Venturi drive created a vacuum on the system, pulled the air through the system, and then shot it right to a flare. Propane was added to ensure that we had a stable flame so that, on startup and shutdown, we were burning everything off instead of potentially creating a cloud of carbon monoxide. Nitrogen was added that would, if we had some kind of emergency shutdown failure, we would pump nitrogen into this so that, if this is at a vacuum, we've got a fuel mixture going through this pipe. If we suddenly lose the Venturi or something shuts down, we're going to be potentially drawing a flame plus air into a fuel mix. So we thought that was a good idea. And then we did have pressure release throughout the system going to the exit, out to the exterior wall, through the exterior wall. So when we're going to run the process, we start, as I said, going right through the bypass. When we want to run the plasma, we would begin shutting this gate valve 1, opening the other gate valves, and then passing material through and out to the Venturi. If we want to run the plasma and the catalyst bed, we would open up gate valve 6. That gas blends with the gas that's coming out of the plasma, and ideally we would control the temperature of what's going into that catalyst bed and try to get to the activation temperatures with minimal electrical input. The catalyst bed is heated with electrical heat, and then there's a tube furnace. In the fine print for the plasma, you've got to be around 12 or 1100 C for the plasma to really reform well, which is something we learned, and I had to add this kind of after the initial planning was done, so that was kind of a wake up there. So this is what it looked like when it was all built. The gasifier with the double dump system, the tube furnace, preheating for the plasma reactor, the sample ports located as shown, the catalyst bed with the sample ports going in and out of that. And then again, these are you can't really see it well here, but there's gas chromatography sampling, and then this is the sample port for the gravimetric tar, where we have a larger flow and a larger sampling requirement. So here's the GC, the gas chromatography, the mass spec, thermal conductivity detection or flame ionization detection samples being drawn. Normally we would have an ice bath over these last three so that we would aid in the condensation and capture of the gases. So as you can see, we've got a vacuum on this line, and we're drawing the process gas through these needles. It's bubbling through this series of impingers. It goes through two of them that are actually warm, and then three that are heated, and there's a flow diagram for the hot-cold transfer that's outlined in CEN 143. We call it the European TAR protocol. It's a real nice document that describes sampling of tars and gases from gasification processes. And the key point here is that with one sample set, we could get the head space, which would contain the hydrogen, carbon monoxide, and the other gases, and then we're condensing, as you can see, the liquid constituents of the process gas stream. Here's the gravimetric sampling bench. These are, again, heated and cooled impinger tubes in baths. This is a heated sampling line, and then the heated probe going into the flanged vestibule that we would put on the process pipe at the various locations we wish to sample from. This is a precision airflow meter and a precision totalizing airflow meter. And this little vacuum pump did all the work of drawing the gas out of the process pipe through these impinger tubes. When we did the GC gas chromatography samples, we would just disconnect this tube and then hook another tube up that went to the little GC apparatus. So we kind of got double duty out of this bench. And here's an example of sampling from the process line. This would be downstream of the catalyst bed. You can see the heated probe inserted into that vestibule and the flange connection to the process pipe. And then we would normally have a heater on this valve, but for the picture we left it off. And then here's another example of this is the top of the gasifier. This is where we would put this apparatus to sample from the top for gravimetric tar. And this little port down here is it's a compression tube port that we would put the GC sampling apparatus into. Okay, as far as characterization of the gas and liquid, again, it was gas chromatography, mass spec, thermal conductivity, and flame ionization detection. For the gas samples, we had a plot column, porous layer, open tube. We used an argon carrier gas and thermal conductivity detection. And then most of the work that we did was with the ResTech column, targeted for hydrocarbons and aromatics, and that was flame ionization detection to enable us to look at a few select molecules that we calibrated and tuned the system for. A lot of work had to be done on the method development and the calibration, and I don't think Mike Keychek's on, but he did a lot of our GC work and did a really nice job in terms of getting his calibration samples at 2,500, 5,000, and I think he did 10,000. And then he ran a check with everything at 7,500, and you can see he came out pretty good on the calibration curve. For the gravimetric samples, we would take those 6 large bottles from that bench I was showing earlier, and it's all prescribed how you mix them together and basically boil them down in a rotary vacuum evaporator, and then you weigh the residues that are left behind. And one of the problems, I think, is this is really tuned for heavy tars, and I mean, I guess looking back, you know, we're trying to make benzene, toluene, xylene, which are kind of in the same boil point range as the isopropyl alcohol that's used in this. So it's kind of I'm not sure what to say there. It's just hard to see what you're looking for when they have the same boil point range. I guess the net of it all. As far as temperature and flow rate, we had to know what was going on in the system. And for that, we went commercial. There's a company called All Power Labs that makes gasifiers and have some pretty interesting concepts and equipment that they sell. And this is one of their process control boards, which really worked perfectly. In other words, for the most part, 16 thermocouple inputs and a number of delta pressure inputs for rotometer or flow rate measurements that you could see a typical run. This is only some of the thermocouples that you could see going through startup. Then we got everything together, we started running, and then of course the issues and opportunities to innovate and overcome the issues starts popping out of the woodwork. Our feeder and level sensors work good on wood chips, but when we had the paper and plastic, primarily the paper shreds, tended to blow around in the gas flow. And of course you got tar going all over the place, so they tended to glue to everything and block the line of sight for the level sensors. So we were kind of stuck running blind after the first day or so of operation. And then what also happened is that these things bound up, and we had to add an air-driven rod with these little rakes that would pull this material off of the incoming plug and drag it down into the gasifier, and then they also mixed it up. Here's the diagram of what we put on there. This is the rake that's going to pull the material off as it's pushed forward, and these lower ones tended to mix the material up and move it to the other side of that downflow tube. The other thing we got out of this is a little benefit. We have a grate interface nut that would give the grate a little kick every time the thing cycled up and down, so that it kept the ash moving through the system. I don't talk about it, but we had a kind of an elaborate ash removal system where we had basically a vacuum source. We could open up these air intake valves and draw the ash out and do a clean out while the thing was operating. The other issue, next one, was the plasma. The plasma runs at several thousand volts. I guess I should have known this, having worked where I have and run into a few EMI issues in my day. We noticed whenever we ran the plasma, when we started up, that the board wasn't taking any more data. And then when we shut everything down and started back up, we noticed that the thermocouples that were anywhere near the plasma were dead. The channel that on the board that connected to those thermocouples was blown out. And if you think about it, a thermocouple was spitting out a millivolt reading, and your board is amplifying that and turning it into a digital output, and we damaged the board. So we wound up replacing the board. Before we replaced it, we used the remaining channels to figure out what we had to do to protect everything, and we wound up putting toroids all over, putting shielding and grounding, and what really was unfortunate is that it kept us blind at the critical point downstream of the plasma. There was just too much energy going on there, and we couldn't get a real good reading on temperature coming out of the plasma, so that kind of created some heartache. The plasma had its own set of issues too. Originally, they wanted to run at 1000 C, and then when we showed them this, they said, well, we should probably run at 800 C, because what was going on is we were eventually melting this after a few hours of operation, and the amperage and the voltage started to go out of spec, so we shut down, cooled down, and found that this had occurred. So we had this repaired by Drexel, and I couldn't believe that we lost this thing in UPS. We had to get it remade by Drexel. So this was several months of downtime for us. Hard to recover from. The other thing we were noticing too was the flow rate was low. I discussed extensively with the guys at Drexel what we should do, and we did get okay to put an extra hole in the thing to allow gas flow. Originally it was coming out of these small ports, and we couldn't get enough flow to really even detect it in our flow rate system. So unless we were really drawing a super vacuum that was overloading the compressor and everything, we couldn't get enough flow through this to do much. And then the danger was an unstable arc. We didn't want to remelt that plasma, or I'm sorry, the ceramic insulator or anything else. So we were kind of gun shy on running the thing to the full potential. And what we found is that the air injection was the high pressure point in the system for some of the plasma runs, and as a result, we didn't really get process gas to the plasma. It was flowing backwards towards the venturi and the other way around to the venturi. So no process gas got there in some of the experiments. The catalyst bed, again, the idea was to use the plasma to initiate a controlled combustion to heat the catalyst, to heat the gas going to the catalyst. Again, we don't want to use electricity if we can avoid it. Let's just try to burn some of this raw syngas that's got the tar in it to get us to that 800C. And the issue that we had was when we were doing these experiments with the catalyst bed was overheating. And that should be an endothermic process, the catalyst process. But as soon as we had the process gas open to it, we were very rapidly getting 800, 900, 1,000 degrees, and we basically panicked and thought, wow, this is bad, we better shut down. And we played around with it, and eventually later on we figured out that, again, we're injecting air into the plasma, and it was flowing in both directions, giving us an air-fuel mix that when it hit the catalyst bed at the 800C, apparently it was enough to initiate combustion, or maybe it was even combusting in this line. Again, we were blind with this respect to the temperature. We wanted to be around 1100, but we couldn't really tell what was going on. Not until we got into the catalyst bed and had thermocouples there, we could see that we're getting hot faster than we should. But as far as results, after getting through these hiccups and issues, we did make tar, we did make gas. We did flare it off in the flare. I mean, our feed was 70% wood. We wanted to get a stable char bed and bed. We don't want to, this isn't a gasifier project. The goal was to make tar and analyze it. So we put a significant amount of wood in there, but then also a reasonable mix of paper and cardboard and plastic, and then dry dog food to simulate a military base waste as best as we could without having the odor of true garbage. The results were that we had lots of tar. Depending on the sample port, we could have tar running out all over the place. One of the interesting things was that we grew a stalagmite at the flare. That I'll talk about the analysis of that later. But what we found was the airflow was about 10% of complete combustion. We looked at how much feed we were putting through there per day, what the airflow reading was. We did approximate ultimate analysis, so we know how much potential combustion energy is there. And what we found was that less than 10% of the airflow was going through the thing for complete combustion, which is consistent with literature. And it was significantly less than 10%. It was about 9.4%. And I think the reason for that is all the extra plastic material that we had in there that was basically fractionating and leaving the gasifier. We didn't really get enough testing to show that we were cracking heavy material, heavy tars into benzene, toluene, xylene. I mean, we could see the different chemicals captured in the GC mass spec vials, but we didn't get enough significant data that we could say, yeah, we were cracking this to benzene, toluene. We had a couple series of runs in August and again in December where we were, these are where the issues and overcome operations were taking place. Basically, we were making hydrogen throughout. To summarize, coming out of the gasifier, we had 3 to 11% of hydrogen plus carbon monoxide plus methane. When we went to the plasma, it was down to 2 to 6%. And coming out of the catalyst was 0, and that's just operator error on our part that we didn't have the parameters optimized. We had that extra air going into the thing from the plasma, and it was just basically combusting all of the energy stream in the catalyst bed. December, after we had everything fixed and back together, we had another series of runs. Again, this is where we had the air from the plasma causing flow in both directions, and you can see that because we see all this extra oxygen in there. We see very little hydrogen. Then going into the catalyst, again, most of the data showed there's very little hydrogen, a lot of oxygen. And then coming out of the catalyst, for a couple of the runs, we did see significant amounts of hydrogen coming out, very little methane and some carbon monoxide. Probably the highest percentage of hydrogen and carbon monoxide was after we did that scrubbing step where we were pumping the gas out of the top of the gasifier, going through the JP8, and then ejecting that gas into the GC mass spec vials. And in this case, we were seeing about 13 to 23% hydrogen, carbon monoxide, and methane. After the plasma, we saw 0 again because of the operator error I think we had going on, and then we blended that basically pure air stream with the bypass of the plasma. That went into the catalyst bed and then came out at about 7 to 9% hydrogen, carbon monoxide, and methane. The sampling from the gas sampling conclusions, we did see CO and H2 throughout. Again, not enough statistics to really get good numbers, but some interesting things. We see hydrogen and oxygen in the same vial, which does imply a problem. There's a sampling problem. And when thinking about it in retrospect, we're sampling with a stronger vacuum from a system that's already operating a vacuum. So these GC mass spec samples are going to be under vacuum. It's going to tend to want to draw in air. We would immediately, pull the syringe needles out in a manner that we didn't have a direct open path. We would disconnect from the process pipe, pulling the syringe out of the vial, and then immediately pull all the syringes out of the vials and then cap them with an aluminum foil tape to try to seal them off as best we can. But I think part of the problem is if you have a gas sample at a vacuum and you do your GC mass spec or GC sampling with a syringe from that vial, the syringe is going to be at a vacuum as well. So when it withdraws from the vial, it's going to tend to want to draw in some air as well. So there's one thing learned the hard way. And there's other things we could do about dead end pre-evacuated volume vials or bottles, and somehow equalizing them with inert gas prior to the GC operation. What kind of confirms this sampling issue is that the highest hydrogen and carbon monoxide and the lowest oxygen and nitrogen is on the scrubber effluent. That's the gas that's drawn through the scrubber by the pump and ejected to atmosphere, or in this case pumped into the vials at positive pressure, or at least near atmospheric pressure. So there we didn't have what I just described, vials up that are existing at a vacuum. Second highest H2CO is at the gasifier top, and again that's a low system vacuum part of the process. The closer you get to the venturi, the higher the vacuum is going to be. So that could be what's going on there. Arc instabilities, the melted ceramic insulators, and the fear of further damage resulted in incorrect plasma gas flow, and that's I think we were pushing the process gas away from the plasma. Anytime we were trying to really open things up, the amperage started going up, the voltage started going down, which is what happened the first time we melted the ceramic insulator. So it was a little gun shy that we're going to destroy the system again, and we didn't really get to understand that well enough at that point in the process. And again, then the rapid rise in the catalyst bed, I think, resulted when the air plus raw syngas entered and combusted rather than reformed the way we would like it to. Okay, moving on to the liquid sampling. And again, these are the GC mass spec vials, the liquid phase of those. Here's our our calibration sample showing pretty good results. Didn't see what we'd expected on these early runs in terms of volumes of benzene, toluene, or xylene. Did see lots of methanol and ethanol, much more than we would have thought. and then at the at the bottom of the gasifier we would see this number right here, 400 parts per million benzene, 64 xylene. We wound up having to do some correction factors because of this ethanol. We'd run a blank sample and try to get a correction factor and subtract it. That's why some of these numbers are showing negative, and probably lower than they actually were. That was the August runs. December, a little bit better results in terms of seeing all the chemistry that we thought we would see. Another key point I wanted to make is, we were running the 6 vials. Usually we just analyzed 3 of them because everything was getting captured for the most part in the first vial of the liquid. The only thing that really transferred down through was the methanol and the phenol, which is interesting and kind of unfortunate because that's a toxic material that we would not want to have escaping to the environment any more than possible. So in this run, here's some data at the top of the gasifier. We had 2,000 to 3,000 parts per million benzene, toluene, xylene, a little bit of naphthalene. Going through the process pipe all the way to the catalyst bed, we still have roughly the same amount. It's slightly decreased, which kind of implies we're condensing tar or something's going on with it. But then again, coming out of the catalyst, we pretty much consumed all of it. Again, probably because we had that excess air going into it. This is the post-European TAR protocol scrubbing that I talked about, where we're drawing through the vials filled with JP8. I guess the interesting point there is that we did capture all of the benzene, toluene, xylene, and the phenol in that synthetic JP8, using it as a scrubber. The only questionable thing is the methanol that made it through. The IPA I attribute to using the same system, the pumps, the totalizing meters, and everything else. It's probably full of isopropyl alcohol from the initial runs, and that's what we're seeing here. So conclusion from the liquid sampling, we did see methanol, ethanol, and isopropyl alcohol more than we wanted or expected. We ran blank samples to make a correction factor, and that's what drew some of the samples negative, low or negative when corrected. One thing we can say is the first vial was catching all the aromatics. Methanol and phenol can make it through. We weren't looking through for light alkanes, which I'll talk about later, which is something we should probably have been doing. And the ETP, the European TAR protocol, is where the scrubber that I show, that tar bench, is defined on how to run it and the parameters and temperatures. And what we can say from that is, again, that the JP8, renewable JP8, caught all the aromatics and the phenols in those impinger tubes. And again, nothing made it out of the catalyst bed or the plasma, and I think there was excess air that was burning everything up. For the gravimetric sampling, again, that's the heated tube drawing from the process gas through a flanged connection. The major thing here, I kind of discount this one. The gasifier top only had 0.01 grams per liter, whereas at the bottom we had 0.11 grams per liter. Pre-plasma and post-plasma, it decreased. Here, I'm not sure what was going on, if the gas flow problem probably was. And then post-plasma, we see very little coming out, and we saw that in the GC mass spec that not much made it out of that plasma or the catalyst. Conclusions from that, again, the 626 run is probably not valid. The 86 run, the plasma shouldn't be that much lower than the gasifier at the bottom, and it could be a condensation problem. I didn't really talk about it, but we had preheaters or heat tracing throughout the system to keep the tars from condensing, but some of the samples, when we opened them up, we did see liquid tar, which says we weren't keeping it all in the gas phase. Post-plasma, the fact that the gas and the liquid showed very little coming out, we were destroying it somehow. Same with the catalyst. Again, the gasifier top is running a scrubber with renewable JP8. We did a boil off on a hot plate because we couldn't use the standard TAR protocol rotary evaporator because the boil point of that is so high. So those results are likely a little bit low. And again, we didn't have enough experience to get statistical results and get some good hard facts. I mean, this method is difficult to run. It's very time consuming. And the problem again is that these light quote-unquote valuable tars are going to have the same boil point range as the IPA. So if you're looking for benzene, toluene, xylene, you're probably not going to see them because they're going to flash off and boil off with the isopropyl alcohol. Now, one thing that we did find was a stalagmite underneath the flare. And I guess I'm running out of time here, so I'll go quick. But we think that we were condensing the process gas following the Venturi drive. Recall we're pulling the air through the system with pulling the process gas through the piping with compressed air. That's going to cool the gas at that phase and probably knock out or condense the higher molecular weight elements. And we happen to have a hole in the flare that this stuff was pouring out of and then condensed into that little stalagmite. We looked at it with FTIR, and we see that it's pretty much an alkane material, straight chain hydrocarbon, fully saturated with hydrogen. Based on a differential scanning calorimeter, it's about 30 carbons long, which is really essentially bunker fuel, the stuff we use on boats. And probably there was lighter weight alkanes, but they didn't condense and form a stalagmite, or if they did, they probably would have evaporated away. So that's kind of a big implication that you can take basically the plastic from MSW and turn it into diesel fuel of various fractions. And the unfortunate part is we didn't look for it with the GCFID. It's a heavy molecular weight material of 400 AMU, so it's going to be tough to see with these techniques, but it's probably in there in the GC mass spec if we looked at it closely. This waxy material was soluble in the synthetic JP8. You can see it going into solution here with a little bit of heating. When we filter it, we find it's 64% by weight soluble in the JP8. And I think if you look at the burning of straight chain alkanes, it would probably burn just fine in diesel fuel. Even though it's a longer molecule, I think it would unzip pretty fast in the combustion chamber and give you energy. Some other tests we did, this was kind of outside the realm of the CERTA, but we did a mock tar-laden fuel test. We had an 18 kilowatt diesel engine. We spiked with toluene. We saw some D-rates, but it did, we were making basically electricity with that stuff, even, with excess of aromatic hydrocarbon in there. For a budget, we had $780K. NREL had $120K. We invested in the gasifier up front before the project for some other work that we did. We also had about $250K for the GC mass spec equipment, and then a scrubber I'll talk about in a little bit. We also have some money invested into as well. The transition plan, I really think there's potential with the idea of using an updraft gasifier, like a rotary gasifier, to produce a high tar stream. If we quench it at the right temperature, we could ideally knock out the heavies, keep this temperature still pretty high so that a lot of the lighter hydrocarbons are going to go up into a scrubber. The scrubber would run on the JP8, and again, we could run high temp in this T2 zone and push over a lot of the aromatic hydrocarbon and burn it in the engine, or we could take the liquid phase, do some filtering and purification of that, and run it into a diesel genset. We actually did make a system like this. We haven't fired it up yet, but we did want to propose that for follow-on ESTCP work. And then we are currently constructing a waste energy system here. It's going to be built and run in Owego. It's built down in Baltimore, being constructed right now. And it's basically a pyrolysis and reformation process that uses ceramic balls. We should really get construction or assembly together in earnest in October this year. It's tuned for 9 tons a day, a 250 kilowatt system. Originally it's going to run on wood chips, eventually transfer to MSW, and we do have a port to allow connection of that scrubber between the pyrolyzer and the reformer so that we can try to do what I've been talking about, which is scrubbing tar and making a tar-rich diesel engine fuel. In summary, this was hard. There was a lot that went on in designing and building this little plant. I think a plasma and catalyst are a stretch for a forward operating base system. They're complicated, expensive, and dangerous. You got to use hydrogen, especially if you've got a variable feedstock, and the plasma is going to cause interference problems. We did show that we can make hydrogen and carbon monoxide. We can destroy chemicals like heavier tars and benzene, toluene, xylene in a plasma or catalyst bed, but we didn't really get this optimized, unfortunately. The benzene, toluene, xylene, and naphthalene were captured in the vials. We didn't really look for the alkanes in this, the stuff that was coming out of the flare. There's a plethora of peaks, and I'm sure there's some number of alkanes, C5, 6, 7 through 30 in that mix of the GC mass spec runs. And again, that alkane stalagmite is an interesting energy source. I think it talks about benzene, toluene, xylene from biomass, but I think proper fractionation of non-halogenated plastic, no PVC or anything like that, would lead to a range of fuels that may be valuable for us. And I think the scrubber passing light tars to the engine is key. You could run the engine on vapor phase tars, the benzene, toluene, xylene if the scrubber is hot, and then we could again quench out the heavy high boilers, return them to the gasifier, and then probably just burn them to get rid of them and return that energy. And I think again that is the path to the most efficient energy path, where diesel fuel is being used already, like on forward operating bases. I think we'd probably want to have a dedicated diesel engine, and maybe you got to swap it out on a more frequent basis. But if you save 2 tanker trucks of fuel oil, you're probably economically the same or better, certainly better in terms of targets presented to an enemy. And then there's opportunity there for the engine development, seals and metallurgy. It's the kind of stuff we eat up here at Lockheed. WeGo is coming up with solutions to problems like that. And maybe we want to run on tar-laden fuel only when the engine is hot, so that we're not going to condense as much stuff in there, oil, water, or what have you, or acidic water. And then maybe we only shut down the engine after a purge period where you run on virgin diesel to, again, kind of clear the throat of the engine. And you may need to increase oil changes or add inhibitors or stabilizers. And then lastly, I want to have some time for questions. I personally think there is a greenhouse gas problem in my community here in Owego. We've had 200-year storms and one 500-year storm in the last 10 or 15 years. And I wonder if the algae isn't the solution. If we could grow algae in the oceans and grab it and gasify it or convert it into fuels, that may be the solution to energy and the greenhouse gas problem. And that is all I have.
Okay. Well, thank you, Patrick. Let me ask around. Are there questions? And I'll start off with one. How much work was done on selection of a catalyst bed? You didn't spend a lot of time talking about that, what your interaction with NREL was like, and whether you had an opportunity to tailor your bed.
I'll let Kim jump in, but I know we used one that she felt would be optimal for converting heavier tars to the benzene, toluene, xylene. Would be poison resistant, or would ideally just continue to crank out those aromatic hydrocarbons as opposed to reforming all the way to carbon monoxide and hydrogen.
What we found, Robin, was through a lot of the work that we've done here at NREL for cleaning up tar-laden syngas for downstream alcohol synthesis, which had much more stringent cleanup requirements than what Pat needed, was we just detuned the catalyst, which is primarily nickel, potassium, magnesium on the fluidizable alumina support we get from Coors Tech, so that it was selective towards BTEX compounds. And what's cool about that catalyst is even if it encounters chlorine from the plastics that are in the feed or sulfur from the food that's in the feed, it still retains its ability to make BTEX type compounds, and we were able to demonstrate that as well when we were doing the tar reforming here in our demonstration in 2012 at NREL.
it's not poisoned real easily from sulfur and other things up there.
Yeah, it does. But here's my thought, and it's something that we're still working on a little bit here, is there's probably 2 active sites on that catalyst. And by the way, that's just a general composition reforming catalyst. If you take any of the off-the-shelf materials that are available, not for fluidized operations, but for fixed bed, you'll find a similar proportion of nickel to magnesium, which is what we found works best. But I think what we lose when we have sulfur exposure to nickel, we lose methanation, or the ability to convert methane to more syngas pretty quickly. But the tars continue to reform to benzene BTEX type compounds, even when the catalyst is totally nickel sulfur passivated. So I think what you're seeing is probably an ensemble effect, because the larger tar molecules, the multi-ring compounds lay down on the surface, and so they can react with several sites at once, whereas methane is a very small molecule, so it's more impacted by the sulfur nickel species. But we have hundreds of hours of reforming activity where we take the tars and go to the BTEX compounds on this catalyst that has seen sulfur as well.
Thank you. I guess one more, and I have one more at this point. On slide 29, Patrick, you had a column for helium. Was that something you were adding in there to try to do some quantification, or?
Yeah, that was a tracer gas we were trying to use as a way to keep track of everything that was going on, and we forgot to turn it on.
That? Because that brings me to a question on mass balance. Through using tracers and other methodologies, are you able to kind of get an absolute quantification of trash in and small molecules and tars and everything else out?
Yeah, we never got to that point of getting that balance put together accurately. You said slide 29.
Yeah, one more. Yep.
Okay. Yeah, that was the initial intent, was to have an additional way to balance everything, but we never got to that point in analysis.
Okay, so you tried it, but you were not able to use that to develop a real quantification.
Correct. Yeah.
Okay. So around the room, as it were, the virtual room, any questions?
This is Mark Pepe. I have a couple.
Okay.
Hey, Patrick. I was wondering if you guys looked at the maximum percentage of polymers you can have at one time processed within the gasifier?
No, we just established 70% wood, 10% plastic, 10% paper, and 10% food products as a standard starting point. We never really looked at tuning a gasifier to handle a high plastic load. We just wanted to generate a tar stream that was consistent.
Okay, thanks. Did you look at the what the total reduction would be when you look at your weight going in versus the weight of the ash coming out? Did you figure that out?
No, we didn't really weigh the ash coming out. We didn't really think to do that at the time. But there, in terms of conversion, it was pretty good. There was no evidence of very little evidence of char or things like that, partially burned stuff coming out. So I think the main thing we used to balance that was the airflow going in, the feedstock going in, and then comparing that to the ultimate approximate analysis, and determined that it was the airflow was 10% of what would be required for complete combustion of the feedstock going in.
Okay, thanks. Just one last one, and I don't know, I'm just throwing this out there. Do you think you could possibly use this to get rid of energetics on a forward operating base, sort of like a D-mill operation?
You mean like explosives and...
Yeah, that kind of stuff?
That would all come down to the gasifier design, and this was just a steel pipe that basically we were using. We did some analysis of that for some other proposal a while back, and I think the determination was that if like a small round, a 223 round or something like that, you could probably throw in a gasifier, you'd hear a pop, and as long as it's a reasonably thick steel wall, there'd be no danger of a projectile coming out. But I wouldn't want to try it with anything, much bigger than maybe a 50 caliber or something like that.
Sure. Okay, thanks.
Okay.
Anything else? And then one last one from me, and that is with regard to water. The food and other, I guess it was pet food, but was that wet, or did you have any moisture content in your feedstock?
We had it all pretty dry. Yeah, we didn't. We had everything sitting indoors for several months to stabilize. I guess we never really measured the moisture content of the wood, but in general, it was pretty dry material, and that's kind of another evidence to confirm why we were able to get 90% conversion. I mean, if you start getting much moisture at all, things change.
Right, and in the real world, that is the problem they have, is that if you're looking at cafeteria waste and stuff like that, it is kind of wet.
Yeah, I think any design for something like this, you'd want to have, engine exhaust or some other heat source to dry everything out as much as you possibly could.
Okay. Well, I do encourage you to continue to work with some of the folks who, Steve Cosper and even Chris Martin and others who are working in this area. I'd encourage you to continue to work, collaborate, if you will, share ideas, and hopefully at some point in time we can solve this difficult problem.